Okay, so the problem statement tells us that Tom is 1 meter tall and Jerry is 5 meters tall, and they are on the Earth, which is a perfect sphere. The radius of the Earth is like this really big number, and the Sun, we can assume that it's a point, which it kind of is because it's really far away. And we want to find that, so Tom and Jerry are standing on the equator at the same spot, and we want to see what difference in times that they are able to view the Sun. So this is a problem in 3 dimensions, and and since like 3 dimensions is really complicated, we want to simplify this down to probably 2 dimensions. And what's logical to take as a cross section is a cross section that's like horizontal. What I mean is like if this is the Earth, because like Tom and Jerry are on like the equator somewhere over like here. Say it's logical to take this cross section because that includes Tom and Jerry, and like the Sun, which is over here. It includes all of them. So it's pretty logical to take that cross section. So let's draw the Earth and Tom and Jerry. Okay, so that's the Earth, that's Tom, that's Jerry, and we can just let the center of the Earth be O, of the cross section, of course. And then now all that's left for us to represent is the Sun. So since like days are caused by the Earth's rotation, if we look at to like not overcomplicate these things, we can take a reference frame of the Earth, and then let's make this, and then since the Earth rotates, that makes it so that our reference frame that we take is just that the Sun is going around the Earth, which seems counterintuitive, but if the Earth, but then if we say that, like if we fix the Earth, then instead of it rotating, the Sun is rotating. So we can represent the Sun's orbit by another circle around the Earth. That's pretty big. Okay, let's let that be the Sun's orbit. The radius of the orbit actually doesn't matter, as the Sun makes a complete orbit, quote unquote orbit, at a fixed rate, which is 1 day per orbit, or 24 hours per orbit, or whatever you want. And since you want to find like the difference of their daylight, like the daylight they get, we see that all we need to do is draw a tangent from their point to the Earth and intersect that with the Sun's orbit, like so. Like that. Let's let these be T prime and J prime, and then we see that the difference in time they get is the amount of time this is, the amount of time it takes for the Sun to bridge this gap times 2, since that also happened on this side. If this is like sunset, then this is if this is sunrise, then this is sunset, and vice versa. And then the way to solve for that is trying to find O T prime J prime. And then if we know this angle, since we know that the entire angle, like 360 degrees, is going to be 1 day, we can find the amount of days, or just whatever units of time, of this angle. So because JJ prime and TT prime are tangents of the circle, if we draw the lines to the tangents, those will be perpendicular. And let these points be like A and B. So the first like major observation that we make should be that triangle OAT prime is congruent to triangle OBJ prime. And this is because of HL. These two are obviously both right triangles, and OJ prime equals OT prime because they're both radius of the Sun's orbit, and OA equals OB because they're also both radius of the Earth. And since this is a right triangle, they're obviously equal. So then from this congruence, this gives us that angle BOJ prime equal to angle AOT prime. This angle is equal to this angle, and then if we subtract angle BOT prime from both, we get that angle T prime OJ prime is equal to angle AOB. So essentially, this is good since now instead of finding t prime by j prime, which isn't really related to anything, we can now find AOB, AOB, which is related to a lot of stuff. So now since you want to find AOB, it's pretty logical that we try to find angle JOB, which is equal to if the radius of the Earth is r, I'll do that just as like a shorthand to so I don't have to write like the really big number for the radius. That is equal to arc cosine of r over r plus 5. And that is because and that's because if we look at right triangle JOB, then the hypotenuse is r plus 5 and OB is r. And similarly, same logic, we get the angle, instead of JOB, it's JOA, is equal to arc cosine of r over r plus 1. And these turn out to be 0.07167 degrees and 0.03959 degrees respectively. And if we take the difference, then we get angle AOB, and taking the difference, this was I made a mistake. This was 0.032029. If we take the difference of these, we actually get 0.03959 degrees. And then if we divide this by 360, this yields 1.0997 times 10 to the negative 4th degrees. And then since there are 86,400 seconds in a day, multiplying this by 86,000 yields, 86,400 yields 9.5 seconds. And then we obviously still need to multiply this by 2. So the total difference is 19 seconds.